Okay, so we have seen here how we could calculate the delta G of a reaction by taking the products minus the reactants. Now, I would like you to think about a delta G of a reaction. The delta G of a reaction, you can actually go and look it up on the back of the table, but that is not going to be the delta G of your reaction. It's going to be the delta G when all the concentrations are 1 molar. You'll have different concentrations. You're not going to be necessarily 1 molar. So you need to correct that delta G by adding this term here, RT natural log of Q, where Q is going to be, again, the same expression as the equilibrium constant. That means concentration of products over reactants. Please interrupt if you have questions. So this is kind of saying, okay, this is reality. The delta G is not the ideal. You'll be maybe at a different temperature, or you'll be at a different pressure, or you'll be at different concentrations than the standards. And therefore, you need to correct by adding this term here. So when a reaction is in equilibrium, the delta G of that reaction has to be equal to 0. Otherwise, it would not be at equilibrium. Remember that equilibrium happens when the reactants and products reach their respective levels. And so the rates become the same, the concentrations become the ones that need to be able to make the rates the same. When that happens, then this is going to be 0. And then therefore this delta G of a reaction, let me color it here, this delta G of reaction is not 0, it's the one that in the textbook that you can get from the table or calculate, is this delta H of reaction. Since this is equal to 0, then we can send this guy to the other side as a negative. So delta G of the standard delta G of reaction is going to be equal to minus RT natural log of K. R is the gas constant, and T is the temperature in Kelvin. So those, if you know those two, then you can relate the delta G that you can look in the table and calculate the equilibrium constant. And we can see that this is going to be the equilibrium constant with respect to concentrations. Okay. So there's a relationship between the delta G naught and the equilibrium constant under normal conditions at 1 atmosphere and 25 degrees centigrade. Now, notice that this has a T. So if you, let's say, switch from 25 to 30, this is going to change the value of T, and changing the value of T is going to create a new value of K, because they still have to be equal to the standard delta G of reaction. So that means you can calculate the equilibrium constant at any K. Excuse me, at any T, at any temperature, by using this equation here. So this is an important equation, and you probably are going to solve problems soon using this equation. Okay, and this means at equilibrium. Why at equilibrium only? Because if this would not be at equilibrium, then delta G will not be 0. And this equation here will not hold true. This equation will not be true unless it is at equilibrium. Okay, this is a diagram. I don't know if it makes much sense, but let's just go over it. So we have N2O4. a dimer that is breaking down into two parts, two molecules of NO2. So here are the pictures. Here you have N2O4. So this is only N2O4. And eventually only NO2 here. And the one in between is in between. This is a chemical reaction. So, and it is an equilibrium. So what is going to happen? You can calculate the delta G for the reactants, which are in this case is going to be the N2O4, which is this one here. So you have that. And then you can calculate the delta G for the products, which is going to be this one here. This is where all you see here that's coming from there. So in here, the delta G for the products is that. So the delta G of the reaction is going to be, again, products minus reactants. These are products. These are reactants. So you have a larger value, subtracting from a smaller value, give you a positive delta G for this reaction, which is 4.8 kilojoules. So this is a way of visualizing what is happening here. Are the moles of NO2. So at the beginning of the reaction, you start with no product. And then at the end, you'll have 2 moles of product. These are the moles of N2O4. You begin with 1 mole of N2O4, and at the end of the reaction, you have 0. And this graph here is how the energy changes. Okay, so let's look at again at the relation of delta G naught and K. So remember, this cannot. The relationship of K and delta G, when you say, oh yeah, K is related to delta G, is actually only delta G naught. So a lot of people just in everyday language talk about, oh, delta G is related to K. Yeah, but delta G naught is the one that's related to K. If it's not, delta G naught, meaning under standard conditions, is not related to the K. Okay. So in here we have a value of K that is much larger than 1. And that means that the equilibrium is going to lie. So here we have the equilibrium. Let's just do it like this. So the equilibrium here, if Kp is much larger than 1, that means that this reaction here is favored. This one is disfavored. Why? Because the Kp is products over reactants. And the only way that it can be a much, much larger than 1 value is when the products are much larger than the reactants. And so if you look in this picture here, the products are the red. So at equilibrium, you'll see that most of the equilibrium is going to lie at the product side. Reactants and products, so it's going to be only products. And that's when the K is much, much larger than 1. If the K is much, much larger than 1, that means that when we look at the equation, delta G is equal minus RT natural log of K. If this is much, much larger than 1, the logarithm is going to be a large number, and multiplied by the temperature, and R is going to be a large number. So it means that the delta G is going to be very negative because remember, there's some minus sign here. So, and that means spontaneous, which makes sense. It correlates with the K. The K is telling us that the equilibrium lies this way. The delta G is telling us that this reaction is happening and it's going to go towards product. It's going to lie to it's going to be a spontaneous reaction that is going to transform the reactants into products. But if K is just larger than 1, it's not much, much larger. that means that then the equilibrium is going to lie still towards this side because the K is greater than 1, but there's going to be also a not insignificant amount of reactants, not insignificant amount of reactants. And what if the K is much, much less than 1? So we know if the K is much, much less than 1, that means that it's a very, very small number, which means that the denominator has to be very large. So remember that K is products divided by reactants. So if this is much less than 1, means that the reactants are much larger than the products. And so at equilibrium, most of it are going to be the purple, which means they're going to be reactants. Very few are going to be products. So it is in these cases that we might want to, if our aim is to produce the products, then we want to either change the temperature to change the K and therefore change where the equilibrium is favored. Or we can couple with a second reaction and to be able to drive this reaction forward. So we can use the energy from a different reaction to drive this reaction forward. And that happens a lot in the human body, in biological systems. There's a lot of coupling of reactions to be able to make the reactions that are necessary for living organisms to happen. Okay, so here we have an example of the reaction of nitrogen monoxide with chlorine to produce NaOCl gas. It says using the values of GF from appendix 4, calculate the delta G naught, means the delta G of the reaction, and the equilibrium constant K. So let's go this way. So what we need to do is the first step, we need to calculate the delta G of the reaction by going products minus reactants from using the values in the periodic table. And again, do not forget to use the N. This is like the K, the temperature in Kelvin. People forget that they need to use the coefficients in the balance equation here. Once we have the delta G, then we have this value here, and we can use this equation here. We'll have the delta G, we'll have the R, which is a constant, we'll have the temperature, 298 Kelvin was given, and we can calculate first the natural log of K, and then, so we can say, we can calculate this number here by saying delta G naught divided by RT is equal natural log of K. And then we do an exponentiation, and that will be e to the, oh, sorry, I forgot the negative sign here. So minus delta G naught over RT is equal to K. So what I recommend that you do is to calculate a number here, a numerical answer here, and then use your calculator e to the x function in the calculator to be able to calculate K. Okay. So here are the calculations. So we are going products minus reactants, and we're taking the values from the table. Notice again that in the reactants, there's a 0, and that's because that's chlorine is in its standard state. So you forget and you're using your table, you'll be able to get the value. It will tell you on the table that is 0. If it's a problem and you say, they forgot to give me this, just think about it again. They didn't. You are supposed to know that it's 0, or just try to figure out that is an element in its standard state. So if this will be Cl2 liquid, that's not the standard state, and the delta G is different than 0. delta G of this guy, Cl2 liquid, which is not the standard state, is different than 0. And there'll be, you look at the tables, you're going to find that chlorine liquid has a delta G of formation that is different than 0, while the gas is exactly 0. Okay, so once you have the delta G calculated, then you can use it into this equation. So minus 41 kilojoules divided by R, the gas constant in joules, and the temperature in Kelvin. Again, this is T in Kelvin. Now in this problem, they told you in Kelvin, but they might have given you in 25 degrees centigrade, so do not use 25 degrees centigrade here, otherwise this number is going to be different and it's going to be wrong. So this is the correct number. So that's the equilibrium constant. What is it telling us? Look at this value, 10 to the 7, so it's more than 1,000,000, which means that the products are favored. That means that the equilibrium lies towards this side with very little of the reactants left. So it will be a good industrial process. If you are doing, if you want to make NaOCl, then you can just mix those two, put them into a chamber at 25 degrees centigrades, and the reaction is going to produce almost 100% of NaOCl. So for a large negative value of delta G, implies that there is going to be a large value of K. Okay, so we have looked at this equation and this equation. Now we can combine those two to form this equation here, in which we are going to take this value here and substitute it into delta G. So delta H divided by RT will be, and this one will be delta S divided by RT, but this is T delta S, so the T's are going to cancel out and you'll have delta S over R. And then you'll have natural log of K on this side. So this is the equation of a line. Y is equal M, and X is 1 over T. So I'm going to put, instead of X, I'm going to put 1 over T. So this part is M. This part here is 1 over T. Plus B, which is going to be the intercept. And I think you have done this for those of you doing in the laboratory, which is not most of you. The people that are in the laboratory are coming soon here. So they have done this by calculating the Ks at different temperatures. So they actually found out what the K values were at different set of temperatures. And then they plotted K, the natural log of K versus 1 over T, and were able to get a straight line and find out what the delta H and the delta S for that reaction is. So just by doing the equilibrium at different temperatures, you can figure out what the delta H and what the delta S here is. In this case, the slope of the equation is going to give you the delta H divided by R, and the intercept is the delta S divided by R. So you just have to multiply those two by R, the y-intercept and the M multiplied by R, they'll give you delta H and delta S. There's another way of doing it and saying, okay, so this is a linear relationship. And so if it's perfect, in a perfect world, if I take only two temperatures, so if I take this temperature and calculate, so at these two temperatures, I calculate what the Ks are, then I can get an equation of a line, which the x-intercept, the y-intercept is going to be delta S naught over R, and this one's going to be, the x-intercept is going to be the delta H over R, or I can actually use this equation here, which is the equation of is derived from the equation of the line anyways. And that is, if you have the two temperatures, which you can measure, and you measure two equilibrium constants, you can calculate what the delta H of the reaction is. And so practice this equation. So in general, you are going to be given the 2Ks and the 2Ts, and the delta H is going to be the one that you are going to calculate. So I'm going to put a question mark saying, yep, that's the one you need to calculate in general. Sometimes they'll give you the delta H, they'll give you the K2, the K1, and T2, and ask you to calculate T1, for example. So you have 5 variables, 1, 2, the 4 in red and the 1 in orange. And usually you calculate the one in orange, but they can give you the other 4, any 4 of them, and ask you to calculate the 5th one. A more practical case is going to be, okay, what is going to be the equilibrium constant at this new temperature, which I have never measured? So if you know the delta H, you know the 2 temperatures, you want to measure at least the, 2 temperatures. You know let's say you know the equilibrium constant at 1 temperature, T2, you know the delta H, and you want to know the, so you know this, you know this, you know that. So and then you want to know what is going to be the K at this new temperature. Then you have to calculate K1. And again, you have 4 of the 5, and you can do your algebra and solve for the 5th one. So, okay, let me just check here. Okay, so I'm going to stop recording.